Okay, so welcome back, everybody. We'll head into part 2 here, and part 2 is a lot of these statistical and computational models. We will talk about a lot of the current state of the art for tools. Some of them really come in from computer science, and we'll talk about them from a statistical perspective. I hope to be able to highlight what these tools are useful for, where some of the challenges are, and some of the opportunities for statistics. So there definitely are some open problems. There's not a lot of people working in modeling text from a statistics point of view. Is my sound okay? Anybody hear me?
Yeah, I can hear you, Dave.
Excellent, thank you. Cool, okay. So, move that. The content that I put together is very different from what I would normally do. I'm trying to keep this in the mindset of a workshop, where even when we were thinking about doing this live, we would have been going around helping everybody to make sure they can run it, taking questions from people directly and helping them through. So this is a little different that we're in this format, but I did set everything up so that instead of slides, I essentially have 3 documents, and these documents have way more content and detail than I hope to get through today. There's quite a bit of code that I will run, but I'm leaving this what seems like an excessive amount of content, really so that you have some extra resources, so that people that aren't here can maybe pick them up. I'm hoping that will be useful to have that much detail in there. I will be running all the code directly from my my presentation. So you should be able to see it live as we go. Just one more quick thing I'll throw into the chat, just as a quick reminder, is the GitHub page and the workshop page that's really built off of, it's really built off of the GitHub page. And so I'll just throw those up there. Okay, the GitHub page does have a couple of our data files, and there's one here that I'll be using a little bit later on, as well as all the source code, the actual markdown files that I'll be working with. I'm going to start in with sentiment analysis. So sentiment analysis, it gets used in real life in places where people want to know how are people discussing a topic. So it could be within news articles, wanting to know public opinion on current state of affairs, or it could relate to how to looking at unstructured text about how customers might be viewing a product or a company itself. Okay, so I'll show you how to do sentiment analysis. Quite often this ends up being, people end up using proprietary data, and I think that's where a lot more of the interesting work gets done. But in this case, we'll look at some open source data. This is all through song lyrics. So the main libraries we'll use are a bunch of the standard tidyverse ones, with the exception of Genius. And what Genius does is, Genius essentially is an API to genius.com. So genius.com shows you, they provide lyrics for songs. I've had a hard time finding songs that don't appear on genius.com. Everything I've looked for, it tends to be there. The exception is that sometimes I don't really know the spelling. So whether it's looking for Beatles or the Beatles, I usually have to look at genius.com and figure out what I want to do. So for example, for this, we can take an artist and a song, and we can send it through this Genius lyrics, and this will pull it up, and it comes back with a tibble. And in the tibble, it gives us some useful information like track title, line, and lyrics. So already we're being able to very easily import a lot of text data. It does let us go right ahead and pull down a track list. So this will end up being all the songs from an album. No lyrics, just what the songs are. It also does give us a URL for it so that we could go there and look up more information if we want. We don't, with Genius, we don't actually have to program in any of the web scraping. They've provided this API library, which makes all of this really nice. Now there are a few details that I should point out. Sometimes it can be very fragile. So I'll show you what I mean. You can pull down an entire album. So we'll take Bob Dylan's Desire. And we'll go Genius album. That'll pull it down for the artist, the album. And this info all just gives a couple extra columns that'll be useful a little later as we go on here. Okay, so what we have here, because I've thrown this into table, this tells us how many lines for each song it's been able to pull up. So Hurricane, it came up with 1, which effectively is nothing. ISIS Mozambique, it looks like it worked. One More Cup of Coffee, came back with 33 lines in there. There's quite a few of these where the API just broke. So it can be fragile. This is one of those real world things that happens anytime you're doing any kind of web scraping, whether it be through an API like the RTweet library. Sometimes it breaks, it doesn't give you everything you've asked for. And Genius is the same. So I do provide some code to show how one could work around this. And so in this case here, what I'm doing is I'm again going after Bob Dylan's Desire. I'm taking the track list and I guess it's pre-allocating or defining an object that's empty. I'm not pre-allocating it in the terms of reserving some memory. That would be much more sophisticated than what I need for such a small amount of data. Then what I'm doing is I'm looping over the track list. This stuff here is all just diagnostic, really. I start out just by saying, let's say the song length is 1. And then as long as that song length is 1 and this counter hasn't gone up too high, then I'll try to take down the lyrics. And I'll set the computer to sleep for 1 second. And then I'll look at how much information came through. And if it really is just a single line, then it'll try again. And it'll keep trying until it comes back with a better number. So in this case here, we can run this, even though it is a little bit longer. Some of these songs take a couple of seconds, which implies it's taking a few tries to get through. But quite often, APIs or web scraping, even Nathan had to put in a system sleep command in his, just a little 0.05 seconds or something. This is a full one. Okay, so these songs actually came down, which is fantastic. I seem to have all the information, all the lyrics that I need. So if we take a look at Lyrics Desire, it's a tibble, it has track title. This has 8 or 9 tracks. Just erased it from my screen. Each one has a line, and then it has the lyrics for each line. So this makes for a really easy way to get information from songs. So what we'll do is we'll move into some sentiment analysis. And rather than looking at Bob Dylan Desire, I think the burning question that everybody has relates to sentiment analysis for Justin Bieber albums. So we'll start there. Essentially, did he grow up a little over the years? So what we'll do is we'll pull down Justin Bieber's My World album and his Changes album, which is his newest ones. So this takes a moment to go through. I am getting this data from an API, and I still have to add in the system sleep. But as it loops through, it doesn't take that long. There's 10 or so songs per album, maybe 15. And it does add in a couple of seconds. While that's going through, I should point out there's this album called Changes, and when I get the track list doesn't exactly match what Genius Lyrics needed in order to get the name of the song. And it's just when I go through the track list, there were 2 songs that come up with strange punctuation. There's one person pointing out in the chat, it is good etiquette to add in system sleep so you don't overload the web server with requests. Thank you. You're right. Bots can query a server much faster than humans, of course, and it's something that we need to at least be courteous of. Okay. All right, so we did, it does look like we have a bunch of songs with lengths to them. So there's one error that comes up here, and it's just that there is one song, I guess it's a remix that broke. But as I say in my notes, we're not sad about that, that's okay. For sentiment analysis, the way this gets done in practice is, I guess there's a few standards. One of the really common ones is using a lexicon. A lexicon is basically a dictionary or a list of words that describe the sentiment that's in there. The other way is somewhere where you have a bunch of words or terms or phrases that are already labeled, and you try to build a model that can come out with these, that can try to find them. But these lexicon-based approaches, there's 3 very common ones from within this tidy text library. There's the AFIN lexicon, and this one here is some 2,500 words. Each of these words gets a value for how positive or how negative the word might be. So it is on a plus or minus 5 scale. They're all whole numbers. None of the values are 0. It's assumed that words that aren't in this list would be neutral, and those should be 0. And here we ended up with all negative words just alphabetically. One of the other common ones from Bing Liu and collaborators has 2 different categories, positive and negative words. It has a lot of the same words as the AFIN lexicon. There's a lot of overlap. There are slight differences to how these were set up. Generally, they're set up with a specific purpose in mind, and whether or not that purpose applies to our situation is one of the big open questions, really. With text data, if we're given text, there is no way to separate out data cleaning from data analysis. They're really integrated. When we're working with scientists or other groups and we're given numeric data, we just pretend there's no way to separate out the data cleaning from the data analysis. Somebody took a machine and has a bunch of data from there that went through strange transformations to become often a proxy of what we're really interested in. It's just with text data that's really explicit. There is no way of separating it, and often it's on the often it would be on the end list to try to figure out what's appropriate. The one that we'll use, this is actually a local one. I'm in Ottawa. This comes from the National Research Council of Canada. And this one here splits words into various sentiments. So a word like abandon shows up as in the fear category, negative, and sadness. So there are, this is about 10 categories, including a positive one and a negative one, as well as subdivisions of that with things like fear, sadness, trust, surprise. So this one here actually gives us some fairly fine-grained some fairly fine-grained information here. Okay, what we will be doing, I guess there's, to really highlight some of the issues here, there are words that have emotion tied to them that does evolve over time or depends on the context. A word like sick. Sick was bad, and then it became good, and then it became really bad, and so now we just don't go out. And we can look at how that word sick might be represented within one of these lexicons, and in this case here, it's really taking it as negative sentiments. Okay, so for the part that we're really interested in, coming up with a statistical test here, what we really want to do is consider a hypothesis that maybe there's a difference in the sentiment distributions across songs within an album. So what I'll do is I'll just make some plots, and then I'll get into the statistical test. So what I'm doing here is I'm taking the two sets of lyrics. I'm using mutate, which adds a column where I'm plugging in the name of the album. Then I'm binding these things together, unnesting them or splitting them into words. And then generally we just use an inner join. An inner join on sentiment takes all these unnested words and looks for their match within the NRC lexicon. And it will eliminate words for which there is no match and only keep words where they do match. And then within there, I'm grouping by albums. So I'm looking at just within my world or just within changes. And then I'm counting the sentiment. And I will make a plot of that. Okay. So what I have here is the proportion of words within an album. It's the column is an album. We have changes in my world. And the different colors are the proportion of words associated with one of these sentiment categories. So for example, the bottom one is trust, which suggests in my world, there's a lot less trust than there is in changes. This blue one here that's kind of big is sadness, which seems to have gone down between my world and changes. This joy category is about the same, but this green one here, it looks like disgust has gone down and maybe anticipation has gone up. So at least visually, we are getting that there may be some differences here. So what I've done is I've taken the I have the whole set of sentiments, and I'm just looking at the proportion of all the sentiments that are in each category here. Okay. As a statistical test, the kinds of things that we would do at this point is really a hypothesis test saying, is there a difference in the distribution of sentiment categories between these two albums? The alternative would be there is some unspecified change in distribution. So this ends up being a pretty standard chi-squared test for differences. We're able to take these two albums and think of them as being a contingency table with categories, sentiment categories in there. So I'll use the janitor library to make a table, and I will get rid of the sentiment categories for positive and negative. And that's really just because those seem to be subsets of things like trust, positive and negative are groupings of other categories like trust, surprise, sadness, joy, fear, disgust, and anticipation. So in part, this janitor library does make things look nice, which is most of why I might use it. It does allow us to do things like add row totals or add column totals, and it really does format it pretty nicely. So, oh yeah, I was already in the adorn totals. So that's the total number. Oh, here we go. This one will add in the totals for each category. It builds a table of percentages. That's this adorn percentages. And then if you're adding in something else, it will put it in brackets. So this is a column percent. So 12% of the my world words are anger. That's 102 words. Now at this point, before getting into a statistical test, it's probably important to think, does this make sense to do? Or what is it actually checking? So a chi-squared test like this for is there a distribution in the way that these categories are split up across albums? It's really meant to be taking a random sample of elements and then putting them in these tables. So effectively what that would mean in this context is we'd have to work with the assumption that each album is a random sample of words that Justin Bieber might use at this period of time. If we wanted to do the test, is there a change in sentiment values in what Justin Bieber's doing? Now, if you've taken a look at the raw lyrics from Justin Bieber albums, you might actually think that's quite reasonable, that these are just kind of random words in some cases. So it is important to keep that in mind, what this is really doing and what the implications are. This one here, this part of this afternoon session is the place where it's statistically kind of the cleanest, where we're taking albums. All we have to do is assume that the album is a random sample of words. And I suppose we also have to assume that the sentiment library is reasonable, which in this case, it seems like it probably is. So we can run a chi-squared test on this, and we end up with a very small p-value. There's 7 degrees of freedom because it relates to the number of rows minus 1 times the number of columns minus 1. So we end up with 7 there, and a large chi-squared value and a small p-value. So it appears to be strong evidence of a change in distribution of sentiments between Justin Bieber albums. I leave some extra information in my notes dealing with negation of terms. And the very short version relates to this piece here. So if I have a phrase like, my homemade bread is not bad, the word bad shows up as negative, but not bad makes it not negative. So what I do in the next section, which I'll omit here, is showing how to take pairs of words, n-grams where you have 2 words, look for negation, and then really try to decide if it's something that is still negative or should be changed. In this case here, it doesn't change a lot. Apparently Justin Bieber doesn't use that kind of term a whole lot. So looking at the chat, there's a question, random sample of what exactly? Yeah, so you're right, to rephrase, it says if we had a sample of the entire population. So the assumption that we would have to make here is that if these albums are effectively a random sample of words that Justin Bieber might use in that period of time, these are not exactly an independent sample in there. And it's just because songs have choruses, there's correlations between words that are being used, and things like that. So what I'm really trying to do with this example, partly to show you what sentiment analysis is, partly to take a stats perspective of it, but also I want you to be questioning where the data comes from, what it means, and statistically, what can be done. There really is, as I've said before, there's no way to separate out data cleaning from data analysis. And in text data, that is really quite clear. So in this case here, where we're thinking about the entire population of words, the entire population distribution of words that Justin Bieber might have used in one era versus another, these are about 10 years apart, if I remember right, then one would have to consider these words to be a random sample from those that would be representative. There are other ways that you can do testing rather than a chi-squared test. You could use various permutation tests and whatnot, but it still relies on the fact that your sample has to be good. So we'll come back to this, especially in the third part. I'm kind of going into 3 topics in this one section here. And the quality of what goes in and giving some real thought about what goes into it is quite important, and we'll look at some of the issues that come out of that. It can be really hard to check these things, which is why it's important that statisticians are involved in this part of the process. So the second part that I would like to get into today, after sentiment analysis, involves dealing with topic modeling, or in a sense, clustering of text documents. The third part that I'll be getting into is word embeddings, which is really a way of converting words into numbers where we can do math. A lot of what you end up doing with text data is trying to find a way to convert it into something else. Sentiment analysis was converting words or unstructured text into categories. In a way, we'd call it like building covariates. Other terms that get used would be things like feature engineering. And as soon as we've done that, then we have the capacity to use a lot of our other tools. In some cases, those tools work very reasonably. With the sentiment analysis chi-squared test, it's probably pretty reasonable. With later ones, we'll show you some of the open problems in statistics, and as I get into some of the limitations of what can be done. Okay. So for this second part, I have a new set of libraries. I think in the email that we sent around, I wrote this library LDA with capital letters, and it should be lowercase. Okay. So maybe as I do this transition, maybe it's worth taking a moment to pause for questions relating to sentiment analysis. Maybe that's the best thing to do. So I'll give it a minute here. Take a look at the chat. Okay. So a question, a random sampling of what exactly? We're comparing 2 albums, in a sense, sampling the full extent of words in those 2 albums. Yeah, so we definitely have to deal with random samples of words. And in a way, when we're scraping data like this or using an API, we are able to get, say, everything somebody has written or everything somebody has said. If one other comment about negation and dealing with that. So I do have more in my notes. I have that I've posted on our workshop page. These are the sentiment analysis ones up in here. And so it does go into what I do is I split things into bigrams. Then I look for negation words like not good, things like that. Then it starts to really become context specific. So you could just directly use regular expressions and say words like not bad, that should be good, or stuff like that. And in this case here, what I end up doing is I find all the places where there are negations, using negations that I can think of, and then I use regular expressions to change them. So feel free to take a look at that code. In terms of sentiment analysis, well, with this case here, I split things into categories because I was using the NRC libraries. Some of these others, this AFIN one here, it gives values that are between plus and minus 5. So with that, you could do things like track the evolution of those numbers as they go through, say, a book, and you might treat it as you know, perhaps some kind of like functional trajectory or something like this. There's the Bing one is just binary for positive and negative words. So you would probably treat that one differently. Sometimes people will count the number of positive or negative words and use some sort of moving average window kind of thing. And then you could try to compare a couple of these moving average type curves. In this case here, just because I had a good chunk of categories, it seemed like chi-squared would be appropriate in there. Okay, so I'll jump into topic modeling for the next little bit. And I'll try to give a bit of an overview in that. Again, I have deliberately put more than enough content in there to try to give you an extra resource to go to. I'll try to give you the overview of it, along with where, statistically speaking, it kind of stops, where we sort of run out of statistical tools. So there's this pretty classic galaxy data set, and I just want to show it because what it's really measuring, which doesn't matter for our purposes today, is velocities of galaxies, and there's something like 85 or 87 of them. When you plot a histogram, it does look like there's maybe multiple groups, and so this data set is it's one-dimensional, which makes it really easy to visualize, and it does seem to have a few different groups, which suggests that one way to model it would be through a kind of mixture model. And if you assume these mixture pieces are little normal distributions, then you're assuming that a random sample from this whole distribution is a sample from a weighted set of k normal distributions. It might be that we say k is 3, and there's a little one over here, there's a larger one in the middle, and another little one at the end. There's been some discussion in literature about how many there should be. So in doing this, in having this kind of probability distribution for an individual that falls in as being partly from one distribution, partly from another, this kind of mixture, we can really think about having a kind of group membership that's a bit fuzzier. So if we first think about group membership, you could think about the ith individual maybe as belonging to a very specific one of these groups. It's either going to belong to the low one, the middle one, or the high one, if we have 3 groups in there. So we could take this Z, which would be group membership, and treat that as a latent variable or something that we have to estimate. And if we can condition on that group membership, then our model becomes really easy. Our Y itself comes from a very specific and known normal distribution. So the math then works out really nicely if we include this latent variable, and it becomes relatively easy to do estimation and to do all sorts of things. Come out with maximum likelihood estimators, all this sort of stuff. And this really just goes by taking the original data and expanding it up so that each individual has this group allocation or group membership. And the group membership itself has some probability distribution associated with it. So LDA is a latent Dirichlet allocation. It's a way of clustering. In this case, we're dealing with documents, but it has been used for many other sources, many other things. The original paper is this 2003 one, which is quite good. These are really big name people: David Blay, Andrew Ng, Michael Jordan. They're really big name people in the text analysis. So what I'll do is I'll kind of walk you through the generative model. So the generative model is, the idea is this is how data is produced. So going back to the idea of words being randomly placed, that's where the generative model assumes that your words, your document is a bag full of words. And they really do talk about it like that. These words, each word in there is randomly picked from a distribution with a certain model. And so this is the way it's set up. So if we have W is a word, and your word itself could come from comes from a distribution of values that are used for a specific topic, and words, and a document might have several topics. So essentially one document like this one here, it might be partly about statistics, partly about computing, not much about philosophy. And so it would have some sort of, this document would have some sort of probability allocation or Dirichlet allocation across these topics. So the way we end up thinking about this in a generative way is that each topic, then within a given topic, there's a distribution of words that make more sense. So words relating to philosophers like Hobbes or somebody like this, so that would be less likely in a statistics topic than a word like, say, likelihood. So the idea is we start out by having K topics, and for each topic, we come out with a distribution across all the possible words in our vocabulary. This is this distribution is sampled, and we have some kind of Dirichlet prior on there. So we now have K different word allocations for each of the topics, for each of the K topics. And then for a document that we have, this big plate down here, we do is we sample a topic allocation. So this would be the proportion for this document, the proportion of it that relates to, say, statistics versus the proportion in philosophy. And then now we're getting down to the word level within a document. So for each word, we would sample a specific topic. a single topic. This kind of relates to group membership. Before, we would be deciding if we're at one of the low distributions, the medium one or the high. It's this one here, this Z would be saying this specific word will be coming from the statistics category or the philosophy category. And then once we have that word, then we can sample, once we have that topic, we can sample a word from this distribution across words within a topic. So we call it latent Dirichlet allocation. There's this latent topic that comes out for each word. And then the Dirichlet allocations relate to how topics are split. There's each document is about every topic. It's just maybe in the philosophy category, it hits 0 probability or 0 proportion there. And then the other ones fill in the rest of it. So with this, there's been quite a few variations of this that have gone on over the past 17 or so years since the original paper came out. But the original paper is quite a good one, and I think it's still worth a read. So what we'll do is we'll work with some books. Sometimes it's easiest to look into this latent Dirichlet allocation with an example where anything should be able to cluster these. So what I'll do is I'll take books from H.G. Wells, from Gutenberg, the Gutenberg Library, from Lucy Maud Montgomery, and from Charles Dickens. And then I'll take a subset of 3 books from each author. There's a few pieces that are commented out if you want to try it with more books. The runtime does increase with more books. So Gutenberg Library, the books I've chosen are War of the Worlds, Research Magnificent, and The Invisible Man, A Grotesque Romance. From Lucy Maud Montgomery, she does all of the Anne of Green Gables books. So it's a very different style compared to Aliens Coming to Destroy Earth. And then Charles Dickens' books, these are generally about how rich people need to be nice to poor people. Okay, so what I'll do is these books, the way that I pulled them down from Gutenberg, I'll show you what we have in there. It comes down with the Gutenberg ID, which is a single value for a text. There's the actual line in the book. There's the title. The first one here is A Christmas Carol, and the author. I do want to keep the title and author information, but given that I have 3 books from each author, it does seem a little silly to cluster 9 items into categories. So what I've done is I'm going to split it apart into chapters for each one of these books. So what I'm doing is I'm taking all my books, which are binding them together into 100 and some odd thousand, yeah, about 100,000, just under 100,000 lines of text. And then I'm grouping them by title. I'm adding in a line number, which counts them up within each book, each line that's in there. And then I'm adding another line that's going to tell us which chapter we're in. This chapter works by regular expression, and it looks specifically through the text for the word chapter. Or the Dickens ones, he often uses stave. And then in some of these books, rather than saying chapter 1, chapter 2, or whatever, it just goes for a line that has numbers or Roman numerals. So the little caret here says at the start of the line, it should have the word chapter. Or at the start of the line, it should have the word stave. Or at the start of the line, it should be //D as a digit, and the others are Roman numerals. And so the start of the line should have one of these markers. If it is going with Roman numerals, then, or or digits, it turns out that in these particular books, it's usually followed by either a period and then the name of the chapter or a line end. So this did take a couple of tries to get the right piece to work, and to make sure that it was going to actually find the chapters for the books that I'm after. Okay, so yeah, these results will work on these books, but might need some modifying for a different collection of books. Okay, so now I have this tidy books. And in there, I do have chapters. Chapter 0 is typically the preamble. So in this case, it's The War of the Worlds by H.G. Wells from 1898, even though it is counting lines as well. So eventually what I'll do is I'll get rid of all the chapter 0 pieces. The last piece in this code that I should highlight, I do have filter Gutenberg ID equals 46 and line number less than 33. This is very specific because there's one of the Charles Dickens books that has a table of contents, which essentially breaks my regular expression. It catches that stuff, but not in a good way. So it's like each line is a different chapter, which isn't actually what should be in there. So again, I mean, I'll say this probably a few more times this afternoon, but there really is no way to separate out data cleaning from data analysis. You do have to run some lines, see if it does what you think it does. And my experience is the first time I run it, the answer is no. My regular expression didn't do exactly what I thought, or it works in some cases, but not all of them. So that does add a bit of noise to what's going on. At this point, in my notes, I go into a little more detail on stop words. Stop words, Nathan mentioned them briefly. There's the piece that I do want to highlight is that there are a few different libraries for stop words. There's this one from TM, and then the other one comes from Tidy Text stop words. So the one from the library TM, that's this one up here, and there's 174 words. And this is it's a fairly benign set of stop words that come up pretty often. It's easy to look at this and in almost any context think I could probably delete all of them. And so it's relatively safe in that way. The other one, stop words from Tidy Text, there's several different lexicons. So there's actually 3. There's the Onyx, Smart, and Snowball. And these 3 here have slightly different properties. There's with almost 500, 400 words, something like that. And in some of these, sometimes they feel a little too aggressive for the context I'm after. Sometimes words like across or after feel like they'd be a bit more important. So in the second half of this document, which I'll basically ignore or leave for you for later, I'm working on song lyrics. And song lyrics, I don't have a big vocabulary, so it feels like getting rid of this many stop words is too aggressive. So I don't. You could add in your own stop words, which I do here, and I'm just using the basic set of 174. And then I throw the whole thing into a document term matrix. So a document term matrix is rows are documents, columns are terms. And so in my case, each document is a chapter of a book, and we can take a look at what's in there. And I have some 400 book chapters and a vocabulary size of about 25,000. The sparsity is 98%, so the vast majority is 0. Words like alien or war probably only show up in one of these books, or invisible or Green Gables, things like that don't happen too often. You can absolutely use TF-IDF instead as a way of coming up with stop words. And one place where that would be useful is if you were looking at news articles. And right now, it's hard to find news articles that don't mention George Floyd. So George Floyd effectively becomes a stop word, in which case any clustering of documents looks into kind of subcategories of that type of thing. Now, when it comes to topic modeling, you're actually totally okay with leaving in the stop words. It's in practice, what ends up happening is they just get folded into topics already there. So it just ends up being that the main words for each one of these clusters, the main terms are the, of, stuff like that. Now the model fitting is a part that I do want to spend a bit of time on. Statistically, I find it to be really interesting. The model fitting, what we're really after is, we want this joint distribution. Well, we want a posterior, but at this point, we'll just focus on the joint distribution. A joint distribution over words, topics for a specific word, the topic allocation for a document, and then the word allocation within a topic. And we get this joint distribution, and then we can get at the conditionals or the posterior distribution on some of these terms. Now, when you run this code, and even when you look through that original latent Dirichlet allocation paper, people do talk about using Gibbs samplers. They talk about using variational methods. So this really ends up being a type of hierarchical model. So that makes a lot of sense to think about using these kinds of tools. Bayesian hierarchical tools end up being they sound like they make a lot of sense. In practice, the papers tend to be from computer science, and they do use these terms, Gibbs samplers, variational methods, things like that, but they're not doing what statisticians would really, they're not using them the same way that a statistician would use those terms. So what I'll do is I'll choose one of these. I will take 3 groups, and I'll just run this here. It takes about 11 seconds. So I'll run that, and I'll talk a bit about what's actually going on behind the scenes. In this case here, what it's doing, it's not sampling all the parameters in this model. First of all, that ends up being a lot of parameters. What it's doing instead is it's doing something called collapsed Gibbs sampling. Hopefully I have that down here. The idea is that they're marginalizing over some of the pieces that we otherwise would think of as being quite important. They're marginalizing over the topic allocations and the words within topics. And what they're really doing is a type of Gibbs sampling really just on the Zs. And the Z is what's the topic for that one specific word. That piece we can do Gibbs sampling over. And then when we have our end result, we then can infer or estimate our topic allocations and our words within topics. So the catch is, though, if you really were doing Gibbs sampling, you get a huge sample of these Zs. For any specific word, you get sometimes it's in one topic, sometimes it's in another. You get this label switching problem. And if you want inference on things like words within topics or your topic distribution, with that label switching, you've got this huge multimodality issue. It's any of the inference that you would come out with really ends up being demolished by the fact that we're not conditioning on being in a single one of these modes. This is a highly multimodal space that we're sampling. And it's really hard to even start describing inference in that context without conditioning on one mode. Effectively, you would lose all ability to do inference if you just take a look at all your samples. So that's what people count on in this. They'll run Gibbs sampling, and they'll usually use a number like 20 samples, something like this. And the idea is really just trying to get somewhere close to one of the nearby local modes from where you start. So they're really just using Gibbs sampling as a stochastic optimizer. And being somewhere in the right neighborhood is usually considered good enough. Okay, so the idea is that then you can back out or estimate some of these other parameters. And yeah, so what I'll do is I'll show you a little bit about some of the results that we get by doing this on these books, just to show you that, well, it's a random algorithm. I'm using Gibbs sampling. So I assume it worked. It usually does. I haven't had failures on this specific one. Okay, so there's a couple of matrices that this will really naturally give you by using this tidy function on otherwise the output from this topic modeling LDA command. And what I'm trying to do here is just consider the topics. There's 3 topics here. Those are the clusters. And I'm really trying to get at the words that are inside a topic and find the highest probability words within a topic. So that's what these columns are. There's the topic, the word, and its probability of occurrence conditional on being in that topic. So sometimes it's easier to plot this because otherwise it's just a lot of words and numbers. Okay, I have an error, but I think it's invalid graphic state. All right. I've got factor, coordinate flip, scale, facet wrap. All right. What I'll do is I will just shrink down my ggplot and figure out where that's broke. This is always one of the challenges with, okay, so somebody else is running it from there is just reflecting your viewpoint size. Excellent, thank you. All right, this is always one of the challenges in running something live. Restart R or change the text size. Okay, so let's, that might work. Okay, so I am getting some good suggestions in terms of restarting R or changing text size. Add quartz before, let's give that a try. So I will just move this for a moment and I'll bring it back. That was brilliant. Thank you for that, Robin. Really appreciate that. Okay, so that totally worked. So what I have here, 3 topics. Just by looking at these topics, you see I've got the words and the probability of occurrence for those words. And they're sorted by most common down. So topic 3, I end up with words like Anne, Marilla, old, little, stuff like that. Like that's a very Anne of Green Gables topic right there. This topic 2 said Mr. Old is also in there. Oliver, hand, good. This one, if I was going to guess, it's probably more Charles Dickens. And the first one here, Benham, that comes from War of the Worlds, I believe. Got world, things like that came. So interpreting topics is complex. It's never easy. You're kind of lucky if it works. But it is something that does take a bit of an eye to it. Okay. The other piece I'll show you here is the probability of topic within document. So what I'm doing is looking at each one of my 400 or so chapters and then looking at its topic allocation. Each chapter will be split into topic 1, 2, 3. And then I'm grouping these together by book. And so I'll do quartz again since that worked so well before. I'm grouping them together by book, and I'm making a box plot of these gammas here. This one I think would have worked outside of quartz. It's not as complicated here. Unless I just broke it. Yeah, okay. Okay. Try it once more. Leave that the same size. Okay. So this one at least showed what I wanted. It is a random algorithm. It will be slightly different this time compared to last time I ran it. It does look like this top row here, these blue ones, these are H.G. Wells books. The first one is War of the Worlds. The columns here are for each chapter, what are its allocations across these 3 topics. So we've got, for War of the Worlds, it seems like within all the chapters, it's predominantly topic 1. Invisible Man as well, and Research Magnificent. In all cases, it's predominantly topic 1. The Dickens books ended up predominantly topic 2, and the Montgomery books ended up all in, for the most part, dominated by topic 3. So this was in this really easy case where these books really are about completely different things. It was able to find clusters that, in this case, happen to be relatively meaningful. Topic modeling is one of these things where there's quite a few extra pieces that you need to be thinking about as you go through. So I have a handful of notes that I've called further tricks, and then in this document I get into an example where I'm clustering Beatles songs. So you can try that. The data is on GitHub. I did get the data using Genius, so I feel like it's okay to share in that way. The API is really open. So anyways, within these further tricks, I do mention that some things might be stop words. Words like Trump and George Floyd are in essentially every news article right now. So either what would happen is you would end up with these words as being the most common words in every single topic, or you could just remove them. Essentially, the more meaningful words to describe the subcategories for each one would be a little bit further down in the word probabilities within a topic. This is clustering. There's always been the question of how many clusters, how many topics should we use? And the answer is basically always the same. It's, do we get good separation between groups? And in this case here, the way you do that is through perplexity. And what we do is we take some additional set of data, you split your data into training and testing. And with this additional set of data, you see how well it fits. So we're really looking at the geometric mean per word likelihood over, the number of words in a document. It's effectively, does a new document fit nicely into these topics, and do the words within the document fit nicely within that topic allocation structure? This works really well if your goal is data compression. It tends to choose a small number of topics. Realistically though, it's generally what people do is they'll actually just look at the words and topics, try to interpret them. It's not a big deal if you have too many topics, but it depends a lot on your context. If your goal is to later classify new documents, or to take, say, a whole bunch of police reports, and maybe you want to look for terms related to injuries or violence or things like this, or use of force, then maybe you want enough topics so that you can find at least one that makes sense in that way. So in a very practical sense, I'd say perplexity is maybe not as useful as one might want it to be. And it really depends on what you're going to be using this for. A couple other quick notes in here, things like Twitter. Twitter's short, 240 characters, 20, 40 words, something like that. That's not a lot to work with. These document term matrices, those end up just being very, very sparse. And you end up having a lot of problems with getting anything that makes a lot of sense. There's other tools that, well, I guess the reality is there's still a lot of open work on dealing with these really short documents. So there's a couple of tools that maybe with word embeddings make more sense, perhaps, but it really is still a work in progress. If you want to do inference, the short version is there are some things you can do, but not a lot. Topic modeling, in some sense, coming out with these latent topics for documents. You could think of it a bit like principal components, in which case your principal components often would be really bad to then just blindly put into a regression model to predict something. So what people would usually do instead is to find your optimal rotation of your principal components to do prediction. So there is a whole area that does that with topic modeling. Effectively, it's what's the right topic allocation that'll let me take on this next task of prediction. So it's usually called supervised LDA. And hopefully I have references for that in here. I definitely have some talk about the R libraries that will do this. Going the other direction though, for when it comes to inference, if we wanted to get at how do some covariates impact the topic allocation, that's where we really don't have tools. That's where we have a lot of open problems. And there are papers that have taken the perspective of taking this LDA model, which I'll go back up to, with the data generating process, and thinking, okay, well, maybe I have some other covariates that help define the topic allocations, these thetas, but actually getting inference on them in a statistical sense, like what's the covariate effect, that becomes really hard. And it just comes down to these thetas, these topic allocations. They are highly multimodal. So you would need to condition on having a specific topic structure, and then you could do something. But there's definitely, inference is a place where there's a lot of very open problems in there. At least going in that direction. Covariate effects on topics, or covariate effects on word allocation within topics. That part's statistically speaking, it's still very open. But the other side, which we call supervised LDA, that one it does a lot better. It's just a way of folding this whole system into a generalized linear model, something like that. I do see there's quite a bit going on in the chat, so maybe I should take a moment and take a few questions and take a look at that. Okay, so we've got one. Is the beta in the code related to the hyperparameter in the hierarchical model above? Yeah, the beta in the code, which was their probability of a word given a topic. So that, by the way that they've set it up, amounts to being these phi's here. And they use gamma instead of the document allocation theta, which, to be honest, I find to be very strange notation. I haven't seen that in many other papers. The notation that I've used here is pretty common in the literature. Okay, and then do you think it's reasonable to use topic distribution within each document as a predictor? Great, and a couple of people, okay, so somebody's posted the supervised topic models. Excellent, good. Yay, team chat. Okay, do you have any suggestions on how to approach LDA in parallel computing sessions? Yes. Next question. No, there's a bunch down here. So way at the bottom of what I do, I have a few reference. I have some Beatles stuff there. And then way down at the bottom, I have a few more pieces to read. So there's, in there, there's accelerating collapsed Gibbs sampling for LDA. So this does talk a bit more about that strategy of collapsed Gibbs sampling in this context. There's another one where they talk about pushing this out to Spark. And so that would be using parallel computing settings. There's all sorts of tools to expand it out. There's quite a bit of the sampling. There's actually a lot of really good tricks that have been developed over the past almost 20 years or 17 years. The other reference that I throw in here, finding scientific papers, this one's really neat in an academic sense, of course. This is where a group took a whole lot of journal papers and then tried to cluster them and then come out with what has this journal done and what kinds of things do they publish. About maybe 3 or 4 years ago, I tried to do this on SSC talk abstracts. And there was, I don't know, maybe 100 or so talks that were going on. And a lot of the really common words were things like likelihood or data, and those showed up in most of the talks. And I found that I didn't have a very sort of even spread of the abstracts. It helped me to get some of them split apart, but others, I think the language use, I didn't have enough examples of terms to really be able to pull together things like a lifetime analysis and survival analysis that a human might want to put together. What are your thoughts on using a pre-built model like BERT for topic modeling? Do you know of any good R implementations? So originally, that's a good question. So I did mention at the start that I have way too much content, and I kind of knew that going into this, but I was putting it out there anyways. I do have the next sort of thing that I was going into is about word embeddings. And in there, you could take these word embeddings, basically converting your words into vectors of numbers, and then do some clustering in there and try to look at topics. There are ways that you can do that. BERT is essentially just like a fancier way of doing that. There has been some work done there. I think that LDA is very fast and is a very good tool. So it's the one that I tend to go with personally. Let's take a look. A couple of other good references thrown in here in the chat, so thank you for that. Are those simply the final iteration of the sampler, or are they averaging over iterations? So it's really hard to check that, but I do believe that it's the last, it tends to be the last iteration. And in other people's work, I've been able to look at the way their code is set up, and it seems like it's the last one that they use. And just one sec, my dog wants to leave the room. There you go. Okay. How to deal with new words appearing in the test set or new documents when evaluating perplexity. Yeah, it's a great idea. So a great problem to be thinking about. So in perplexity, what we're trying to do is maximize this probability of a new word given topic allocation and all of that, and looking at how well a new document fits into the model that you built. And so the model that you've built, or the assumption is that you already have the vocabulary that's in there. A new word you would have to deal with somehow. You would have to make it an NA or delete it, I suppose. Or you could assume that this new word just has a very low probability. Effectively, you'd be throwing at it like a prior value of something very small and throwing it into possibly all the topics. I'd have to check, but I think that would be equivalent to just deleting the word, because it really would have then zero effect on this. Ideally, when you're doing test versus training, your assumption is these things come from the same distribution. It's just in this case here, we have these categorical distributions of words. So these things are, we do have to assume that we have all the possible categories in there. Yeah, these, in terms of the multi-core tools, this LDA, I don't think this one has a multi-core approach. And then the other one comes in through this library here. And we use this supervised LDA stuff wherever I talk about that. Oh, it's down in inference. So within this function, this one maybe. This one I think is a newer implementation of it. This comes from library all lowercase LDA, and this is the one that will do that supervised LDA. And now I realize this is probably too small to be totally useful there, but let's take a look. I don't see anything obvious in terms of setting the number of cores. So you would probably need a different implementation than the ones that I've used. Is there any, so equivalence of LDA and non-negative matrix factorization? Yeah, there is. Non-negative matrix factorization is a pretty interesting tool as well. And this is taking a linear algebra approach instead of a hierarchical Bayesian model kind of approach. And they are certainly highly related to each other. Or I suppose there's an equivalence. They're definitely highly related. I have not read that paper, so I think the idea would be to take your document term matrix and then split it into sort of or factorize it into a, say, document topic matrix and a topic term matrix, and that sort of piece in the middle would be giving you the topics. It would make sense that there's an equivalence. It might be that it's a special case where these things are the same. I haven't read that paper. Better metrics to evaluate LDA model. LDA being something that is unsupervised. Realistically, it depends so much on your purpose for it. I have a friend who works on clustering news documents, and their goal is to cluster 10 million or so news documents per day. They use something like 30,000 different topics. And the intent there is really just use a whole lot of topics, and some of these will be very fairly obscure topics, and hopefully that'll be really useful for their case. What they want to do is sort topics so that they can send them to people with very specific interests. And so having more topics tends to be helpful for that, whereas having too few, like in my case, I really saw no topics relating to aliens or invisible people or things like this. And I didn't even have like a Christmas topic, despite having the Christmas Carol or even a ghost one. I would need to have more topics for some of that to make sense, and that just ends up taking longer to run. So I did run this yesterday with 20 topics, and I did end up with one that was sort of the ghost Christmas topic and things like that, and that it did make a lot more sense in there. Can we reproduce a document using the LDA setup? So yes, I suppose the whole assumption behind it is that a document is a bag of words where we actually don't care about word order. So I say yes, as in, if you're lucky, yes, subject to permutation, you wouldn't have to be as lucky. You'd have to be really lucky to have them in the right order. The matrix rises by integrating out the latent topic indicators associated with each word. So I suppose that would be integrating out, I guess this question here probably relates to non-negative matrix factorization and LDA and the way those are related. Cool, and there's a couple more papers there. Excellent, thank you, that's fantastic. So the references in the chat are great and definitely worth looking into. What I'm hoping to give you from this section is maybe a little bit of a sense of what this is doing, but also a sense of where the statistical limitations are and what the challenges are in working with text. Now, I do have, and I'll just kind of leave it there for you, sort of a whole lot more in terms of content for today, and it's all about word embeddings and things like that, which is really like a whole other maybe hour or something like this in terms of workshop. There are a lot of open statistical problems there. Within that context, the one-liner version of the whole thing is you have a way of converting individual words into a vector of numbers, and statistical tests were not designed to deal with, there are currently no statistical tests that are designed to deal with that, with data with these kinds of subtle issues. At the very bottom of that sort of document, I go into the short version of it is that if you wanted to compare two documents, you're just always having significance. It's just like guaranteed significant effects. Not useful, but guaranteed significant. So we've got somebody asking, would you organize another workshop like this for word embeddings? I probably could, in that we already have the content. So if you really want to listen, I'm happy to do that, in that I don't think it would take me much. So we'd have to maybe pick a time or something like that. So maybe we could do that maybe a little bit later on, and we would advertise it through the same types of channels. I'm happy to do that, since we have code, we have really interesting things. There's a lot of really interesting statistical issues that come up. Bias in data sets, the whole issue of is this a random sample of the way words are actually used, or is this a convenient sample? It ends up giving all sorts of issues, sometimes that are really hard to notice. Statistical tests, there's huge challenges, even though they're technically possible. I think it's a really cool area, and there's a lot of neat stuff that's going on. There are very few statisticians playing in that space, and it's kind of it would be a fun place for us to chat a bit and talk about where this is useful, where it has challenges, and where it has potential. This is, you really can't separate out the data cleaning and that from the data analysis, and it just becomes really obvious with text. But there's strange artifacts that come out, but there's some really neat mathematical tools and really interesting computational tricks and stuff like that. It's a neat area for sure. Lots of open problems. Yeah. Okay, one other question about STM. Yeah, okay, like short-term memory. Yeah, okay. Or structural topic modeling. Okay. Yeah, there's a handful of other really good tools that can be used. There's all sorts of, I'd been thinking when you said STM, but like, well, first I Googled it, but then I was thinking about like LSTM models, these long short-term memory kind of neural net structures and things like that. We didn't even get close to talking about any of the neural net tools in here. And they start really coming up when you look at these word embeddings, and then there's a lot more other things that can come out. There's a lot of other pieces to be talking about in terms of text. There's parts of speech tagging. So looking for what are the nouns, the verbs, the adjectives. If I use a word like it, what is it referring to? And in this case, I guess it refers to it, but things like that. There are some really interesting models that are in there. Yeah, the area of language processing really got a huge boost by people in computing to give us the tools that we can actually use. But then now it really is time for statisticians to be stepping in and looking into ways to answer inference questions, or look into issues of randomization and things like this. Cool. So we've also got another reference on more about STM as a way to estimate covariate effects. So thank you for that. That's one that I'll take a look at offline as well. So thank you to everybody who came today. I hope you got your money's worth, this free price for you. The Data Science and Analytics section, it's a new section with the Statistical Society of Canada. We are really hoping to build bridges between statistics, computing, comp sci, people even in applied math, people in analytics. We're really trying to bring together people in a very inherently interdisciplinary group. So please do think about joining. We will be developing as a group, so we'll have more ways to connect in future. In the meantime, I do hope that so we do have links to how to find us. Both Nathan and myself are easily available on Twitter. So you can find us there. We have such cryptic names. I am Dave Campbell and Nathan Tavik.